Why do wind turbines never run away in a storm while a free-spinning fan would? Because a turbine isn't just a propeller. It's a controlled machine that constantly steers into the wind and twists its blades to stay in a safe, efficient speed range, like shifting gears and turning a steering wheel at the same time. Start with the real goal: keep rotor speed near its target. Too slow and you waste wind. Too fast and the loads explode, bearings heat up, blades flex, the drivetrain shakes, and the generator can overspeed. So modern turbines use two big control knobs: pitch and yaw. A turbine blade is basically an airplane wing. When wind flows over it, the blade makes lift. But unlike a plane wing, that lift is angled so part of it becomes a twisting force that turns the rotor. And that twisting force depends heavily on one thing: the blade's angle to the wind, its angle of attack. Change that angle, and you change torque. That's pitch control, rotating each blade around its long axis. At low to moderate winds, the controller pitches the blades to the sweet spot that grabs the most energy. You can think of it like finding the best bite into the wind, enough angle to generate strong lift, but not so much that airflow starts separating and getting messy. But once wind speed reaches the turbine's rated level, the strategy flips. You don't want more power anymore. You want stability. So the controller starts pitching the blades slightly out of the wind to shed lift. This is the key idea. Above rated wind, turbines deliberately waste wind so rotor speed and generator power stay flat and safe. Two pitch positions matter. In a fine position, the blade faces the air like a wing and pulls energy out efficiently. In feather, the blade turns edge onto the wind, killing lift and slowing the rotor. Feathering is an aerodynamic emergency brake. You're not fighting the wind with friction, you're removing the wind's grip. So how does the blade actually rotate? Inside the hub, each blade sits on a giant pitch bearing, driven by a pitch system, often electric motors with gears, sometimes hydraulic pistons. Sensors continuously measure rotor speed, blade angle, generator power, temperatures, and vibration. Then a controller, basically a real-time computer, commands tiny pitch changes every second. In gusty wind, those micro-adjustments happen constantly, smoothing torque so the drivetrain isn't hammered. And pitch has to work even when things go wrong. If the grid drops out, the turbine can't rely on external electricity. That's why many turbines carry backup power, batteries or capacitors, so the blades can still feather to a safe position. There's redundancy too. Each blade can have its own drive and braking, because losing pitch on even one blade can unbalance the rotor and turn a controlled machine into a wrecking ball. Some older turbines used stall control, where the blade shape is designed to naturally stall at high wind speeds. But most large modern turbines prefer active pitch because it's more precise, quieter, and far better for safe shutdowns. Now yaw. Pitch controls how much energy the blades extract. Yaw controls where the whole rotor faces. If wind direction shifts and the turbine doesn't turn, you lose power, and you create uneven loads because one side of the rotor sees a different wind angle than the other. So turbines mount the nacelle on a giant bearing at the top of the tower, letting the whole machine rotate. A wind vane and anemometer measure wind direction and speed. When the controller sees misalignment, your motors drive a ring gear to rotate the nacelle. But it doesn't spin freely like a weather vane, because cables inside would twist up. Instead, it turns in controlled steps, and turbines track cable twist and sometimes do an unwind maneuver to relax the cable bundle. Yaw can even be strategic. In a wind farm, operators sometimes yaw an upstream turbine slightly off the wind to steer its wake away from turbines behind it. You sacrifice a little power on one machine to gain more total power across the whole farm. Now picture a storm gust. Wind speed jumps hard. First response, pitch out a few degrees immediately to dump lift and hold rotor RPM. At the same time, the generator controller can increase electrical torque, like magnetic braking, to resist the rotor smoothly. If the wind keeps rising toward the cutout limit, the turbine feathers more aggressively. And once the rotor slows enough, a mechanical disc brake can lock the drivetrain as the final line of defense. Meanwhile, yaw keeps the rotor aligned so loads stay balanced, but it won't chase every tiny direction wiggle, because yawing too often wears out the gear system. So the secret of turbine speed control is simple: pitch for torque, yaw for alignment, and braking as backup. One controls how hard the wind can push. The other controls how evenly it pushes. Next time you see a turbine turning calmly in crazy wind, What do you think it adjusted first? Pitch, yaw, generator torque, or all three together?